In this video, we will discuss the concept of significant figures. We will go through how one would determine the number of significant figures a particular measurement or value has. Significant figures and the reporting of them is a way to convey to your reader or audience the level of accuracy with which you did a particular measurement. A significant figure is the measured value that you are reporting. Whenever you're doing a measurement, any non-zero value is something that you clearly measured. So for example, the value 536 would be considered to have three significant figures. All non-zero values are significant. The tricky part comes in determining whether or not a zero value is significant or not. Because if we measure something and the value in that particular location is a zero, we need to be able to convey it. But you could also have zeros that are just placeholders. So, zeros that occur between non-zero digits are significant. So for example, 6,703 would have four significant figures. The 6, the 7, the 0, and the 3 are all measured values. The value in the tens place just happens to be a 0, but because it is encapsulated by two non-zero values, we know that it was measured and that the value is 0. Leading zeros are not significant. Leading zeros are values that come before a value but after a decimal place. These are considered to be non-significant values. So a placeholder 0 is located to the left of your non-zero digit in a value that is less than 1. So an example of this would be 0.0043. The 4 and the 3 are measured values. These are both significant. But the zeros that come before the 4 are just there to keep the 4 in the thousandths place. So they are not considered significant. These values here were not necessarily measured. We just had very accurate equipment that could measure down to these two particular decimal places. So these two are considered significant values. These first three zeros are just there to hold the 4 in its particular location, and so are not considered significant. Similarly, trailing zeros are also placeholder values. So zeros to the right after a non-zero digit are non-significant, and this is for values that are greater than 1. An example of that would be 7,000. 7000 has only one significant figure, the 7. These three zeros, we do not know whether or not they were measured and are actually 0, or if they're just there to hold the 7 in its particular location. So we don't know whether this value is actually 7,000 or if it's somewhere between 7,499 on the upper limit and 6,500 on the lower limit. Right? So we don't know what these three values actually are. They could just round our value up to 7,000. So because we don't know for certain what these values are, they are not considered significant. Another example is 32,040 would have four significant figures. The 3, the 2, this 0 that is sandwiched between the 2 and the 4, and the 4. This last 0 here is not considered a significant value. It is merely there to keep all your other values in their correct location. This value here could be a 0 or it might not be a 0. This could be 32,035, 32,044, and just rounds to the value that's displayed, because we don't know if this last value here is actually a measured value. We cannot consider it to be significant. Now, the last part is that zeros that are to the right after a decimal place are considered significant. So for example, 50.0 has three significant figures. The reason why this has significant figures and just 50 would only have one is that by putting the point followed by the 0 here, what you are telling your reader or your audience is that we measured all of these values. In order to write 50, you don't need to put 0.0. So the only reason that you would put this additional 0.0 there is to tell your reader or your audience that you measured the values and that the value in the ones place happens to be a 0 and the value in the tenths place also happens to be a 0. Another example would be 0.0600. So in order to say that you have 6/100ths of whatever you are measuring, you don't need these two additional zeros, right? So they are not, the purpose of them is not to keep the 6 in its particular location. So the only reason that you would write them down is if you're conveying the information that you measured them and you know their exact value and it just happens to be 0. These first two zeros to the left of the decimal place and immediately to the right, but before the 6, these are not significant. These are placeholder values. These zeros are there to keep the 6 in its place. The zeros that come after the 6 are conveying the information that we know what the value is in each one of these locations and that they happen to be 0. Now, because we're going to be working with very large and very small values, sometimes it is convenient to not have to write down all the zeros. In this case, we will use what is called scientific notation. Scientific notation is a method for expressing very large and very small numbers. The general construction of a scientific notation value is some number that has one value to the left of the decimal place, and then how many ever significant figures your particular measurement is, times 10 raised to a particular power. And this is indicating how far to the left or to the right that you need to shift the decimal place to get back out of scientific notation. So your n values are all your significant figures. The a is how far you have to shift it left or right. We would use a plus value to shift the decimal place to the left and a minus value for shifting the decimal place to the right. So for example, if you have 3010, it has three significant figures, right? The 3, the first 0, and the 1. This last 0 is not significant. And so we would leave this out and we would write 3.01 times 10 to the, and then what we would do is show or count how many locations we have to move the decimal place in order to get the decimal place to be directly to the right of the 3. So it starts out here, 1, 2, 3. So this would be 10 to the third. So note the decimal place was moved 3 locations to the left, which is why we get a positive exponent. Another example would be 0.0310. So in this case, we would write it out as 3.10. Each one of these values, the 3, the 1, and the 0, are all significant. But when we're trying to figure out what the exponent is, our value here, we need to count the number of locations that we would shift the decimal place to get into scientific notation. So that would be 1, 2. So we shift it 2 to the right, and so it would be a -2 in our exponent. So this would be 3.10 times 10 to the -2, because we had to shift the decimal place 2 to the right. Note that in both these values we have 3 significant figures, right? They're both 3.01 times 10 to a different value, and the exponent tells us how far we have to shift the decimal place in order to get it into scientific notation. Let's now go through a couple more examples. So our first one, 50,003 kilometers, 50,003 has 5 significant figures, right? The 5 is significant and the 3 is significant, and because the 3 zeros in the middle are sandwiched between 2 non-zero values, we know that each one of these was measured and they happen to be zeros. So these values here, these zeros are all significant. So we have 1, 2, 3, 4, 5 significant figures for this value. If we're talking about 400 liters, there's only one significant figure, the 4. Because we don't know if the zeros here are actual measured values or if we rounded to get to the 400, we don't know if they're significant. So we have to assume that they are not. If you wanted to display a value of 400 and show the number of significant figures, that is an example of when you would typically use something like scientific notation. So you could write this out as, let's say, the 4 and the first 0 were significant. You could write this out as 4.0 times 10 to the second power, right? And so that would show that you measured the 4 and this first decimal place here, the one in the tens place. But as the value is written, the 2 zeros here are placeholder values, and so we only have one significant figure. Our next example, 0.04450. The first 2 zeros are placeholder. The last 0 doesn't need to be there, and so if we're including it, that means that we measured it and the value is a 0. So this value as written has 4 significant figures. The first 2 are placeholders, so they do not count. The value, the 0 after the 5, the only reason it's there, or the only reason that you would include it, is if you're trying to tell your reader or audience that the value is significant, you measured it, and it just so happens to be 0. Our next value, 100 centimeters to 1 meter. This is a definition. Anytime you have a definition, it's considered to have infinite number of significant figures. A lot of times the definitions should actually, instead of having an equal sign, have a triple equals. This means defined as, but a lot of times you'll find on the web, and perhaps even in some of my own written examples, that the equal sign is used instead. But if it is something that you know is a definition, like using the metric system, there are exactly 100 centimeters in 1 meter. It is considered to have unlimited number of significant figures, and so later when we're doing mathematical manipulations using significant figures, we would not take this into account. But if you're counting up the number of significant figures for this particular equality, it would be said to have an unlimited number or an infinite number of significant figures. Again, the reason for this is that there are always exactly 100 centimeters in 1 meter. You cannot have 99.99 centimeters in 1 meter. It is a definition. There are exactly 100 centimeters in 1 meter. Our last 2 examples, 1.000 times 10 to the third. This has 4 significant figures. Because we're writing it out in scientific notation, any values that are displayed in scientific notation are significant. That is one of the advantages to using scientific notation, is that we can easily convey the number of significant figures that we're working with. So these 3 zeros here, we don't actually need to include them to write out our value in scientific notation. We could have 1 times 10 to the negative third. That is perfectly valid. But by saying that it is 1.000 times 10 to the negative third, we are conveying to our audience that we measured each one of these values and they happen to be 0. So this will have 4 significant figures. Similarly, 3.050 will also have 4 significant figures. The 3 is significant, and the 0 here is significant, the 5 is significant, and the last 0 is also significant. So it doesn't actually matter what the exponent is that the 10 is being raised to. In terms of figuring out your number of significant figures, you just look at the value before the times 10 raised to some power. It's the values here will tell you how many significant figures you have. Each one of them is significant. So the bottom one here will have 4 significant figures.